I thought that digitalization was a topic that might have been of interest for an Eawag seminar. With the COVID crisis, we talked about COVIDization of research. Many people moved and said, let's work on this because it's important, relevant, but it's going to allow me to do things that I would not be able to do before. Same thing happens with this digitalization approach. The hype that is around it makes that you can get funding for research to do things you wanted to do. We're not able to because you couldn't convince funders, companies, cities to do modeling and control. Now we call it digital and everything is possible. It's also a danger. If you don't deliver, then you will soon be seen as the person that tried didn't work. And I've done this before, so I've worked on artificial intelligence first time just after my PhD, after my graduation, in fact, in '88. Artificial intelligence became visible, became interesting. First hype was complete disaster, nothing worked. The data were not good, the tools were not ready. In 2000, I had a PhD student that said, I would like to do something with neural networks. And there was quite some movement in the area. So we tried again, and after 6 months we said, no, this is jeopardizing your PhD, let's do the classic modeling and continue with that. But now it's different. So my feeling is now is that the data collection has been stepped up quite a lot with all the efforts that people have done. The tools, the Googles, etc., made tools available that are really functioning now. And we see nice results. And I can, from our own research, I will show you some of the nice results we have with these methods, and that's why the practice things come into play. The picture you see is Quebec, and before it was end of September, now it's end of October with climate change, so the colors come later, because that's how nature reacts. This is the campus that I'm working on. Let's see how the progress works. Yeah, first, the names you see is all the people that have been working on the cases I will present you. Okay? It's a good team that we have with exciting people. Okay. I'm going to first talk a bit about theory and concepts and things that are going around when you hear the word digitalization. And the first thing that pops up is that we have this digital water, we have smart water, we have Internet of Water, we have Water 4.0. And when you see that happen, you think, okay, this is a hype that's dangerous to go in. You should be a bit careful with hypes because they can be over in 2 years' time. I had a déjà vu, as I mentioned. I had been going through this and was a bit reluctant in the beginning to go in. But then I saw the potential, and the first results we got said, yeah, this is good. Let's work on this and we can prove that this is systems that work. So I think it's beyond the déjà vu only. We will see new things coming up. And I don't know which term will survive, but it seems that digital water is the one that we'll see. I'm a person that likes clear terminology, so I would like just to make sure that we talk about the same thing. So these are digits. And you see already a problem with the terminology because we count from 1 to 10. When you program, you count from 0 to 9. Digitalization could be about using your digits. That's what we do as well. I've only started recently to use a smartphone, but... This is also about binary code. And recently I've changed my favorite number from 37 to 73 because of this guy, Big Bang Theory. This is his favorite number. And there's a very nice episode where he talks about the goodies of 73, why this is his favorite number. And one of the things is that it's you write it binary, it becomes a palindrome. It's 1001. If you read it in verse, it's 100101. 73 is the 21st prime number. 7 times 3, all these things. If you ever want to see it, it's a 1.5-minute thing that is just, writers of these comics are really interesting. They find all these things that are related to the 73 number. Digitalization is analog to digital conversion. If I have a microphone there, it transforms an analog signal from vibration into a digital code, and ones and zeros come out of the system. That's digitalization. Digitalization or digital transformation, I found one definition. It's the use of digital technologies to change a business model and provide new revenue and value-producing opportunities. It is the process of moving to a digital business. That's what companies are doing. They are going to the digital water because these are giving them business opportunities. It gives them more value. So that's what we call digital transformation of the water sector. When we talk about industry, then it's interesting to see why they would do this. And there was a nice presentation at the Young Water Professional Conference in 2019 in Toronto by Wesley D. from Tourism Technologies. And he basically gave a list of things why industry is interested in digital transformation. First, economics. Internet of Things connectivity and functionality are very cheap these days and will probably get much more cheaper in the future compared to earlier technologies. And when I started, it was connecting, just the cabling was already very expensive. Right? The building blocks are in place. We have sensors all over the place. We're measuring so many things and it will not finish. We're just adding sensors. So information is there. We're drowning in data if we're not careful. We want systems to become more robust and digital because it gives us advantages. Connected systems can be updated quite easily. They can be updated in real time. Just send an update of your program running and it has improved. It makes it flexible and therefore we can handle unforeseen circumstances in which these systems are embedded. This is so from Max. Decentralization of treatment is enabled because once you're able to connect, you can have your experts sit in place, work on the different systems. You don't have to be present remotely. It's becoming practical and to manage these and make them robust. Workforce. I don't know whether you realize, but people that have moved into the water business are now turning my age, your age, are leaving. Peter is leaving. So many people are leaving. The workforce is basically going up and we don't have the replacement for them. So one way of dealing with that would be to automate certain things, to replace people by machines. That may not be nicely accepted because people say when you say you're going to replace people, they're afraid of their job. But if there's job loss and you can't replace, you need to do something. And this one could be one of the systems. So the art of keeping systems running needs to come from expert systems rather than the experts, remote access, telepresence, etc. Product as a service. So you don't sell an equipment, you sell the data coming out of the equipment. And that whole paradigm is coming into place and it requires, again, people that will service all these equipment that we put in place. Connectivity will be very important. Just a number, just to give you some sense. It's about money. This was 2015 predictions. I don't know what it came up with, but it's hundreds of billions of dollars in the water sector, drinking water, and the same thing. Wastewater and water were evaluated as approximately equally important in terms of savings that you could get by digitalization. Where are these savings generated? Well, first of all, you should continue what you did before and take advantage of digitalization to make it better. So you can do your design of your equipment, your treatment facilities, your sewer systems. You can work with better process control. I just want to highlight this little document that is pretty old. It's dated from almost 50 years. And if you read that, it's really maybe frustrating, otherwise very comforting that all the goodies that come out of control are still very relevant. They give a number of things that are good for the systems, and there's still those that you use as an argument for saying that process control is important. And digitalization makes it just more easy to do and better to do. If you look, however, at utility management, so I don't know how it's run here, but I think it's utilities and you have regional organizations that run the water systems. These systems become more complex because we integrate them more and more. And to be able to then find out what you can do, how to improve it, it becomes really important to structure the information. And big data that we collect and data analytics tools that we have now allow us to do a number of things. It allows us to think carefully on long-term planning because the information, the historical data tells us where things are going and what you can, and then the models can allow you to predict what's going to happen. You can confront customers with the way they work and live. I still remember the first times I heard about the billing or the invoicing system in California where people were shown where they were located in the behavior of the similar families. And it makes you think about the use of water, for instance. Infrastructure optimization. You have systems in place, you have data about them, you can find out what you can improve. And you can also use it to use proactive maintenance. You know, some equipment is starting to fail, it starts to show some noise on the data, it starts to be like hesitating to do what you want to do. You can go in and send the people out to repair rather than going out all the time and see whether there's something to be done. To make the right decisions, the right people need to have access to the right information at the right time. And by the way, we also say Deloitte, but it should be Deloitte. It's a French name. Okay, I'm going to go back to my first period here in 2017. The 3 months I was here, we did a horizontal scan. Some people are present in the audience. I was the only one with a tie on the picture, which is not normally what I'm doing, but this is a picture we took. It was a paper we wrote in Environment Science Technology that basically compiled 3 months of discussions here at Eawag about what are the elements, among others, about digital transformation, censoring, new data sources, and the urban storm and wastewater system. I just want to highlight that digitalization was already there in 2017, so things are coming. Because in the paper, we basically found out, or we tried to find the most important emerging topics, meaning that they are important research fields and they are places where we are feeling insufficiently familiar with that. We need to learn a lot about them. They're important, but we don't know enough. So this is an emerging topics. They thus require further research, and oh yes, we want to do further research. Half of the topics of those 10 were really around data. It was some of them were generating data. What can we do with this? Or there was other things. We wanted to have data to make certain decisions to improve things. We wanted to have more data and good quality data. So there was data pull topics, there were data push topics. And you can read the paper if you want, of course. There are challenges, plenty of challenges. I only have a smartphone since 2 years, right? Many people are suffering from digital anxiety, are afraid of what's going to happen to them in their lives, in their work environment, because it's changing. It's very easy. I think all of us are probably liking to have a stable environment to work in. If it's changing too drastically, we feel uncomfortable. So that's happening with the workforce. There's still a lot of problems with standardization, about storing information to just communication of data. It's not completely good yet. Data quality is a big issue. If you talk about the data pipeline, it's full of obstructions. It's full of clogging of the data pipeline because there's garbage coming through the pipeline. It's leading to problems of garbage coming out, and that is completely ruining whatever beautiful idea you might have to use the data for. Chris Villet was here for quite some time, and he's now chairing the task group that is looking at data and metadata and how to store data. And this is a nice figure he made. I think I'm going to reuse it. So you have these nice tools that basically transform data into useful information that you can then work with. Big data, you can dump everything into the machine, and the machine will be so clever that it comes up with the questions with answers to the questions we have. This is just this little filter that can clog if you don't make it right, that basically make that the data don't come through and that you don't have the nice information you have. So that just the idea of making sure that you clean up the data before you use it, before even you train your systems, is very important, because otherwise we get the wrong work. Public safety, another challenge. I've heard about water utilities that were hacked, that were ransomed. You don't want to have that in Virginia. You don't want this to happen, right? They kept the system running because luckily the SCADA system and the really critical was off the net, but everything else was gone. Reporting, payment of people, meetings, all was gone for 3 weeks. I don't think they paid, but they had to do everything backwards. And we see the same thing with power suppliers that get ransomed. Hospitals, we know that's happening. Universities that get hacked. The other university in Quebec was hacked. We're out for 4 weeks before the email system. Everybody went on Gmail suddenly. It's terrible that these things happen, and water is like really critical. Energy is really critical. So we might sometimes think that this is more problematic than nuclear power. A nice thing I discussed with Peter at the time was, if you see how science contributes to the progress of society, then there's the traditional route where we acquire knowledge, we learn, we study, we synthesize, we follow a certain paradigm, we shift the paradigm. Often that is domain specific. You keep digging into the domain. And that's the hard work to get progress. If you see what happens with data analytics, they take methods from completely any domain, apply it to the data you collect, which are important, and then things come up, improvements get. And it seems, or the impression we might get, is that this is the easy way forward. Just collect more data, apply these methods, and you will make progress. And you may even learn, if you make a clever use of those artificial neural networks, you might learn something about the system. So the fear that we both expressed at the time was, will there still be place for mechanistic models? Do we still want the activated sludge models, the hydraulic models? Do we need them? Or is it something that we will be the last generation doing it? So we have an exponential growth. Well, exponential, it's interesting to see the difference between genetic algorithms. Oops, I don't know how to use this thing yet. It's almost a linear increase in number of publications, and longer it happened like when I was talking about this was in the end of the 80s. Machine learning is much later. It's 2010, 2012 it starts, and it's very exponential. So there's a difference in pace depending on maybe the use of the word. It might also be a word thing. However, if you look at the water sector, this is a slow sector. You cannot do a PhD and think that your results will change the water sector. It just takes more time. It needs at least a postdoc more to see the result of your work. It's 10 years, 10 to 20 years to have a change. And it's very frustrating for some of us. Because the installed base of equipment that we have is there to last. We built it to last 20, 50 years. You don't want it to be changed. The typical time constant, which is the dynamics of a critical element of a dynamics, is a time constant, is 10 to 20 years. When you talk about data transformation, every year you have a new iPhone with new capabilities. Digital transformation is talking about 1 year to 3 years. It's really changing completely. Maybe it's good that it's slow in the water sector because we talk about security issues. You don't want to mess with water. And there's ethical issues as well. And talk about intelligent toilets. Soon we will know everybody what sickness is coming. And we'll spread it around the world because the data will be sent to some central system and we may have problems with that. So there's a lot of ethical issues as well with water. Just thinking about the COVID analysis with wastewater, we had a group of people work on ethical issues. Because you look into people's lives and you might confront them with things that they don't want to hear or know. However, there's an important paradigm shift. Before this happened, like before 2015, I would say ICA is instrumentation control automation. You really had to be very convincing to talk to utility managers to say, yes, we're going for this. You had a few early adopters, but it was really hard. Modeling, the same thing. The consultants are now doing it, but it took years of hard work to convince that this was before it came practice. So many of the good ideas never made it up because they were bottom up and the managers didn't care. The hype made something. Our mayor talks about digital. Yeah. Everybody in management wants to be involved in a digital transformation because it's cool. And they see the uses, of course, as well. So it's now top down, which means that there's money available, that there's directions given. You see chief digital officers being installed to make it happen quickly. They don't want to wait a long time because the next election comes. And the personnel is empowered to do new things, to take risks. And now it's being said, if you have any doubt, just try. Before you tried, and as soon as there was any doubt, it was out. I've done things on full-scale industrial plants where we just got the permission to try it out, and we tried, and after 2 days the system was out because the operator said, I don't trust this. It does something different than what I've been used to do. And management said, okay, we stop. Even though, in principle, it should have worked. So let's grab this opportunity with both hands and make digital water happen. And people know that I'm a fan of Formula 1 racing. It's hammer time. So Hamilton, when he goes for the racing, has to do an extra effort to win. In a very short period, they say it's hammer time. So it's hammer time for digitalization. This is not the end of my talk, though. This is just the introduction. I'm going to give some examples of practice from our work. And I'm going to do it along this line. I think this is a paper or figure that you might see, hopefully you might see, because the paper is quite popular. It's something that one of my PhD students made, and he worked a lot on the graph. You see the data pipeline coming from data coming in. You can use this. All the sources of data coming in, you transform the data, you store the data, you extract the data mine, you model, you create knowledge, you create insights, and you go to action. That's the data pipeline. I'm going to show some of the things that we've done. And it's about wastewater. I'm a wastewater person, so coming from the tap or the cloud until the river. wastewater is nasty. This is what you sell. This is what the equipment providers sell us. Very nice sensor that can do, it will change the world. And after a week, they look like this. And they lead to noise and outliers and faults and gaps in data. And that's what we have to work with, right? So sensors are not perfect, even though the sellers try to convince us. So there's bias, there's drift, there's complete failures of sensors, there's noise. They fail and need a lot of maintenance during operation. The data need validation before you use them, so that has to be done in real time if you want to use them for direct decision making. And if it's a lot of data, you want to not have a person doing that, but you want to do it automatically. And if you have high frequency sensors, you can get these sensors to say something every second to you. That may be hard to deal with. So what we've done in the group is we focus a lot on data quality because the garbage in, garbage out is really difficult. You cannot demonstrate the goodies of digitalization if your data handling is not done well. So Yanelsi Alvarez, who's now the chair of the ICA specialist group, by the way, which I'm proud of, she worked a lot with us. She was a postdoc with us, and she worked on a method to get from raw data to quality, high quality data, validated data, using different methods. And one of the things was this, what we call the Alvarez method, is basically an analysis of the time series to find out outliers and smoothen the data that you can then work with that signal as a reasonably good signal to look at data features and find faults in them. Every time we got a new sensor, though, we needed to call Yanelsi to work on it because her expertise was needed to tune the method. So this is not feasible to bring it around in practice. So the way it works is that you basically have the green line is the result. All the crosses are outliers, are not trusty data. And you get some idea of where the data are good, where the data are poor or doubtful, or where the data we know it's not good, it's not valid. So this is just a data series. 80% of the data are out, which is good. Typically, data series in wastewater quality, you have a dropout of 5 to 50% of the data, or just not usable, which is a lot. So what we did was to replace that method with a neural network approach, an LCM, long short-term memory model, where we don't need Yanelsi anymore. We don't need a new person that did this. The only thing we need to provide is somebody telling us that this part of the data is good data. These are looking like good data. And then the system learns by itself what good data is, similar to what we do in principal component analysis. You say, these are good data. It learns properties from it and then applies it to new data to clean up, etc. This data preprocessing leads to faults, gaps. It may just be that gaps are there because something went wrong, but it could also be that these data are not trustworthy, so you get gaps. And then you want to do a data filling because you need continuous signals from many other things we do. So how do you get those green lines? You interpolate, that's the simplest thing, just straight line or even just an interpolation. You can have another signal that is correlated value that allows you to predict what the green line should be. You can just keep the value, as I don't know any better, so just keep that value. Or you can replace, and this is probably the better method is to replace the value that is created by a model that tries to collect a lot of information about the signal you're trying to reconstruct. And there machine learning is again a method that is very useful because it is able, that's what it learns to do. So data gap filling is something that we've been using in our work on the data quality part. I have 3 of those bubbles that I'm going to do. I want to talk about Influent generator. If you do wastewater treatment modeling, you want to do simulations under situations that you've not seen before. You want to do simulations over long term because you want to see how this will work in winter and summer and high flow event, increased loading, whatever. So you want to have the main disturbance of the system, which is the influent. So it's about flow rates, rain, snow melt, groundwater infiltration that come to you, and then the pollutant concentrations that come from runoff from household industries that will change things. And data collection is really difficult. If I embark on a measurement campaign with people, it's a lot of planning, it takes multiple people, it takes not one day, it's weeks of preparation and work before you get the data set that can help you identify what the influence of that treatment plant is. For some of the applications we need I would like to have hourly data, because some of the dynamics are at that resolution. I have diurnal effects, I have weekly effects, I have seasonal effects. So you would like to have a 1 year, 1 hour data set on multiple variables. That's just impossible, right? So what you try to do is to, with limited data, focused experiments, you're going to collect information and then you will generalize using models. That's an influent generator. The PhD of Feli has just been published. I'm not going into details. The main thing is that we've trained a system that in the end only needs rainfall data because it's combined sewer systems. It only needs rainfall and temperature data to predict what the influence will be. And we've demonstrated this to work at 3 full-scale systems in Quebec, Bordeaux, and the other one is Paris. And it's it's not just, it's a PhD work, right? So it's a lot of work to get there. And there was some experience, but it's neural networks and then special versions of it that apparently are able to learn enough about the system and can give you good generation of long-term. I can generate now, you give me 100 years of rain time series and temperatures. I cannot. She can generate the time series of influent flow and composition. Just gives you examples of Quebec. This is the moment that the plant was built, very nicely. So this is 1.5 years of data flow. You see the rain is dropping from the air, right? That's why we do it. So rain intensity and then the flow, and you see, of course, snow melt. A month of suffering for the treatment plant operators because the 3 meters of snow must come through the sewer system. Cold water, so really hard. And then you have sometimes very rainy periods in October, at the end of summer, you get this big dilution effects. So the black line is the measurement, the blue line is the model. It's pretty good. So this is concentration. You see that concentrations are constant, dry weather. This is daily data, so it's daily predictions. Very constant, except you have dilution. So if the flow is good, normally your model will be pretty good for the concentrations as well. You see the same effects of dilution. Ammonia concentration, just some information about this is not measured every day, so you cannot train it for the weekends. There's no weekend data, except for the few weekends that you collect measurements, and then you fill the gaps with this model that gives you information about how the weekend will be, and also considering if it's raining in the weekend, which it never does. Let's see at how we use the data. In process optimization, I'm going to talk about model-based predictive control, which is now the new thing. It was there 20, 25 years ago, we talked about it, but with the digital twins, it has become really something that got a lot of momentum. And as I said, digitalization of research, many people that were in control engineering are now going digital and applying these methods to fill the model that you use to predict what the future will bring, and where you can use that information to optimize your process by manipulating certain pumps and valves and whatever. I have 2 examples. One is from disinfection. Jeff Sparks is one of I'm lucky person to have a PhD student that works at the plant. This is his plant. And whatever he does is tested directly. He gets so much trust from his organization, he can try out things directly. He just got his model predictive controller working at the full scale to change the aeration system. Now, he did first this disinfection prototype because it was a bit simpler in terms of concept. So this wastewater is reused for replenishment of the groundwater for drinking water use. And you basically got a lot of data. We call them features in the neural network world. So you have a lot of features, time of day, flow, stability, etc. And you put this information in that's coming out of the system all the time to predict what is the dosage rate of hypochlorite for disinfection. GPH is gallons per hour. If you work in America, you have to learn those other units. Okay, so this is real life. This is the really observed dosage of hypochlorite that they've done on this. It's 1 day, I think. This is what the trained model would have said that would have happened, given the other information. So you basically say, this information comes in, this is what the model would say you have to do, and the great thing is what they did, right? On the normal operation. So this is the new thing. That leads to this result in residual hypochlorite. So you obviously have the 0.5 or 0.7 milligrams per liter they want to reach. It's not optimal because it's a bit too much. You want this. So they could improve and say, okay, with the model we can use the model now to say what should be done optimally to reach that flat line, like optimal control. Now here it doesn't make a big difference. You don't gain money with this one. Here it's different. This is another day. So the other day is the model would have done the same thing, but have said the red boxes are very close to the gray data. but the result is not good. You're just overdosing this chlorine coming in at way too high concentration. So the model would have gone the red line, the model-based controller, which you can implement then and basically and save chemicals or make sure that it's always good. I'm going back to my more normal wastewater feeling because disinfection is not my field of competence, I would say. It's more biological process modeling. So we have these models that are established, people trust them, design plans with, think about optimization, but this is done offline. You don't have these models running on the plant, or very few cases where it's running on the plant, where operators use it to get informed and do it and decide things. The main reason is that you cannot update these models online. You need an expert sitting at the computer to manipulate certain things, and it may take hours to get, or days to get a model adjusted to reality, because reality changes. You have a model, you make a model, and then reality changes because biologist says, oh, I'm having a bad day, we're doing things differently today. And your behavior changes, and therefore the control action you would take for that system that has changed will be different than what you do with this model that is outdated. So you want to update that model. So I guess that in a few years' time, we will all agree that hybrid models are the way to go. What is a hybrid model? It's using a first principles model, which has extrapolation power, which is the backbone of our understanding. And then you have a data-driven model that makes sure that if that system modifies a bit, we can capture that and correct the mistakes that are in the first principles model. And there's multiple approaches. This is theory that exists. It's always like this. The theory, before it gets into the water business, it takes a long time. This is 2000. The theory is that you can use it in series, so the neural network produces information that will be put into the first principles model, and that correction will happen through that input, extra input you bring from the neural network. Or you do the parallel, where you have the data coming in, you push them through the first principles model, gives you results, and you have a correcting term that you add on to the output to make the output fit reality. This is applied on a small system in Paris. So Paris is 9 million people. We're looking at a plant that treats 5 million people. One of the biggest plants in Europe. And we got the chance to, we're not playing on it, but we get the data, we can prepare, and the operators will take some time before they accept this, what we're proposing, but we're going there. It's a complex system, it's biofilter systems, very compact, very intense, and complex because there's 40 parallel links, right? And they change the number of biofilters in operation, so it's really complicated. To model it, this only mechanistically was already one PhD student working on it all the time. So a digital twin is a copy that runs in your computer. And a hybrid model is a mechanistic model and a machine learning model. And they interact with each other. So what you get is influent measurements, actions you do. You collect data from the real life to do that. And you send this through the two models that will do something with it. So the mechanistic model will predict what happens in the different reactors, will predict effluent quality. The machine learning model will do the same thing. And we even can give the machine learning model the data that comes out of the mechanistic model, because this is calculating in real time, so we can give it what it's currently doing. While we train, the training we do is to compare the data from the treated water. We want to have a prediction of the effluent quality of nitrate, ammonia, COD, etc. in treated water. So we basically try to make sure that the model, that the mechanistic model, that will have errors. We will not have a perfectly calibrated model. It will not work perfectly. That we have the errors, that we look at the residuals that we see between real life and what the model says. We use that to train the machine learning model. So the machine learning model only has to learn errors. It doesn't have to learn the whole process, which makes it relatively easy for the system to learn, because the whole nonlinearity of the process is taken away by the mechanistic model. They are powerful. You might need some internal documentation of the mechanistic model to also feed into the machine learning model. For instance, some properties internal in some of the reactors that you might want. So it's not only the effluent data, what you really want to predict, but also some internal variables that you want to give to the machine learning model that it knows what's happening, what the state of the system is. And then you have an operational model. You have a model that collects the data from the real wastewater with an influent generator eventually to make it work. You send it both to the mechanistic model that will generate information that will go into the corrector model, the machine learning corrector model, and you will have the green line that will correct what's coming out of the mechanistic model. And you have I'll show you, an improved and more robust model. Just to tell you how quickly these developments go, The mechanistic model making was a full PhD to get there. And even part of the second PhD that is now working on it. The machine learning person work was 1 year. The data were cleaned up. That was the big thing, because that was done for the mechanistic model. But the whole setting up of the machine learning model was 1 year of work. So you cannot have PhDs anymore on machine learning modeling. You have to do something more than that to have a PhD. Okay, results. Black line, black dots are the data. This is calibration, so that's the easy part, I would say. It's always the easy part. You see that the blue line, which is the model, is not that good. The reason is because it's a compromise. This model has to do ammonia prediction, nitrite prediction, and to off-gas analysis. So all this is so you make a compromise. The model cannot do better than this if I want, otherwise I will lose complete prediction of the other variables I also want. So I've distributed the error of the model. That's what it can do. And we are happy, yeah, given the complexity of the system. This is what a hybrid model does in calibration. So now this is, everybody will say, that's easy. Oh, come on, you have all these degrees of freedom in the neural model, that's fine. But you have to get through this to get to the validation part. So this is the validation. Of course, the blue model can't do better than the calibration model, right? Can't expect that to be better. But the question was, can the validation pass? And I would say yes, right? So this is validation of the data. So your hybrid model has the extrapolation power, has the backbone of the mechanistic model, and is still correcting pretty well because it knows what to correct and what the situations are, because it has seen enough differences. And now we're replacing these controllers for aeration and methanol dosing, which is spanning this. You can imagine if you treat 5 million people, this is lots of money going in. So now looking at how to improve those controllers with these machine learning models or the hybrid model in the loop to make that the methanol dosage is better or less costly and that aeration is better as well, and giving less energy consumption and giving less N2O emissions. Now I'm at my end. So there's digital transformation taking place. Finally, the challenges are not small, but the results are very worthy. The data collection remains, I think, a very big point of attention for me. These tools have become sufficiently mature, I think, now, and I've had some experiences before where I would not have said this, and they can be used in many different practical situations. Just if you have a problem, think at least about, can I tackle this with this type of tools, and to great benefit. Training of our water professionals will be key. Our engineers that come out of our program will have to learn about Python, what that is, and what is a neural network, and how you train, what is calibration, testing, validation, what can you use it for. And I am still very careful not to overpromise what all these things can do, just underpromise and overdeliver. I think this is how we can convince the mayors and the other ones that will give us money to do research and implementation of these things, that they will still be working with this type of things in 5 years. Because it might be over. You have a few very negative things and it might close everything down. But I don't think it's going to happen. Okay? That's the story I wanted to bring. I hope there's some questions.